the class of systems of differential equations is way too large. So we will first study a subset of systems on which we pose some restrictions. We will require linearity of our system, and on top of that we require our system to be homogeneous. These restrictions allow us to make some analytical progress, which is good. And furthermore, the properties and solutions of linear and homogeneous systems will help us to tackle more general problems. So let us see what linear and homogeneous means in this video. So in general, we have for a system of differential equations x1 prime equals some function of x1, x2 and so on and t. And also for the others. Xn prime equals a function of x1, x2 and x3 and up till xn of t. Now first of all we will take n equals 2 for convenience. But this is just to avoid all the notational clutter. Like the ideas also hold for n equals 3, 4 and so on. But just to avoid the rubbish we will take n equals 2. Now, what does linear mean? Well, linear means that our right-hand sides are linear in x1 and x2. So t may do whatever it wants, but the right-hand sides have to be linear in both x1 and x2. So what does that mean? Our f1 of x1, x2 and t has to be some rubbish of t times x1 plus some other rubbish times x2 plus something which only depends on t. And similarly for second function is some rubbish of t times x1 plus some rubbish of t times x2 plus some other rubbish which only depends on t. That's what linear is. So linear means linear in the dependent variables. Now, what does homogeneous mean? Homogeneous means that those g1 and g2 are both equal to 0. So that's what we mean with homogeneous. You'll see already with these numbers here that a matrix is coming shortly. And there we are. We can rewrite the system over here as a matrix equation x1 prime x2 prime equals f1 f2. And due to the structure here, we can write it as p11, p12, p21, p22 times x1 x2. That's this part times x1 x2. And then we have some g1 g2 over here. So we can rewrite our system of differential equations, if we are linear, into a form x prime equals a times x, where a is a matrix depending on time, plus some vector g of t. So that will be the general form of our system of differential equations. So let's look into a few examples. So first example, now is this first example a linear and homogeneous? Well, it looks linear. This one is linear, linear, linear. However, this part here is x1 times x2. So that's not allowed. You have to be linear in x1 and x2. So a function of t multiplying x1, for example. So you cannot do x2 times x1. So this one is not linear. Second example, is that linear? Well, for the first equation we have t cubed times x1, so that's okay. A minus 2 times x2, so that's also okay. Plus a t squared, so g1 equals t squared in this case. And second equation, the p21 would be 1, the p22 would be minus 1, so that's okay, g2 equals 0. So in this case we have a system which is indeed linear, however it is not homogeneous due to the t squared over there. Now if we leave out the t squared and go to example 3, then we have a case which is both linear and homogeneous. Our p11 equals t cubed, our p12 equals minus 2, the p21 equals 1 and the p22 equals minus 1, and the g's are 0. So in this case we have a linear and a homogeneous system. So note, this linear means that we are linear in the x1 and x2. So there are still t cubes floating around here, that's fine. Linear is purely for the x1 and the x2. So now you can recognize when a system is linear and homogeneous, and a big advantage in that case is that you can rewrite such a system as x prime equals a times x plus g of t.